Hello. The purpose of this video is to explain the central limit theorem just as quickly and as kind of simply as I can. So let's give it a shot. All right, so we have a population and it could be distributed anywhere. And what distributed meaning is when you take data from that population and you kind of put it in a number line on a dot plot, what's the shape of that dot plot kind of look like? And if there's whole bunches, can you then kind of like talk about the area of the shape this would be bimodal, right? You could have something that looked kind of skewed up that way. Something that was uniform. We'll talk about uniform things. So each one of these would stack up. There's 10 people here, 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 so on. So there's all these different shapes. The one we talk about the most is this normal curve. Right? That means that there's a mean in the middle, and most of the people kind of surround around the mean. Right? So what's kind of really cool is regardless of what kind of shape you have, if you were to take your population, here's your whole population, and instead of plotting a single person on the number line, you were to take a sample of certain people, and then you would calculate the mean of that sample. There's sample one. And then you put that mean on your number line. And then you would do it again, a different sample, sample two. Take a mean two and put that mean on your number line. And then you do a sample again, different sample, sample three. Take the mean of that sample, put that sample on your number line. You would do this over and over and over again. All different types of random samples, just one after another, and you build a distribution. This is called the sampling distribution. And the key thing with the sampling distribution is that every point does not represent a single data person, a single person. Every point represents a group of people or a group of whatever we're measuring, group of trees or whatever, and it represents a statistic from that group. So is it the mean? Is it the maximum? Is it the minimum? But it represents a statistic from the entire group. Instead of just one person, it's not the height of one person, it's the mean of a group of 20 people. Right? That is a sampling distribution. Now, the cool thing happens with sampling distributions when you start talking about means in particular. Let's say I have this very simple uniform group, right? 1, 2, 3, 4, 5. 5 people, 5 things in this group. It's uniform. Notice the shape is complete. There's one. It's a uniform group. Notice as well here, if I were to figure out what the mean and the standard deviation of this group was, I would know 6 divided by 3. All right, so let's do all of the math. Here's the population mean. This is the whole population. Population mean is 1 plus 2 plus 3 plus 4 plus 5 divided by 5, which is 3. Makes sense, right? Right in here. Okay, now, trickier, population standard deviation. Population standard deviation. Right? So we're going to take 1 minus 3 squared, all right, plus 2. I'm doing this all by hand. Kind of crazy. And I don't have the technology right now to kind of speed this up for you, so you'll just have to kind of bear with. And then we're going to divide it all by 5, right? Because this is the population standard deviation, not 4, but 5. And then we're going to take the square root of that whole thing to get standard deviation. So if I do this, this is 2, so this is 4/5 plus 1/5. You see, that's 1 squared is 1. 0/5, 1/5 again, 4/5 again, 5, 10/5, 2, square root of 2, right? So that's 1.41. Okay, everybody good with that? Okay, so I am now going to take a sample size of 2. And I'm going to take every possible sample size of 2 that I can take. So I'm going to write these down for you. I'll pause the tape just for a second to write them down so you don't have to watch me write them all down. All right, so you'll notice that this is every possible sample size is sample size 2. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5 with replacement. And there are 25 total. I'm going to take the average of those. 2 divided by 2 is 1. This is 3 halves. This is 4 halves, which is 2. This is 5 halves. This is 6 halves, which is 3. Sorry. This is 3 halves. This is 2. 5 halves. 3. 7 halves. 2. Looking at averages. 5. 3. 7 halves. 4. 5 halves. 3. 7 halves. 4. 9 halves. This is 3. 7 halves. 4. 9 halves. 5. I'm going to plot these on a number line, just like we talked about. Goes from 1, 2, 3, 4, and 5. It's the same range. We have 1, 1. We have 1, 1.5. We have a 2, a 2.5, a 3. That's the first column. Second column, a 1.5, a 2, a 2.5, a 3, a 3.5. Third column, a 2, a 2.5, a 3, a 3.5, and a 4. Fourth column, a 2.5, a 3, a 3.5, a 4, and a 4.5. Last column, a 3, a 3.5, a 4, a 4.5, and a 5. You will notice that we have gone from something that is uniform, looks like a square, to something that is bell-shaped, looks like a mound. You also see that the average of this, if I were to take this average, add them all up, divide it by 25, that you would see that this mean is at 3. So the mean of my sampling distribution, which we would write as this, the mean of the means, is equal to the mean of the overpopulation. That is the first piece of the central limit theorem. The second piece is that my standard deviation, and I'd like to go ahead and do this for you real quick. I'm not going to do it all by hand. I'm going to throw this into a calculator and or into Excel or whatever way that you calculate standard deviations. But my standard deviation is going to be 1, right? It's going to be kind of crazy, but it's going to be 1. I'm going to use sampling standard deviation. So I'm going to throw this into a spreadsheet real quick. I'll pause it so you don't have to wait. So I put all of these numbers into an Excel spreadsheet. I encourage you to try it out. These 25 numbers, put them into column A. And column B, you're going to have it equal STDEV.P, because this is the whole population. I did every single possible sample of sample size 2 here. So you're going to use the standard deviation one and go from A1 to A25, and that's going to give you the standard deviation of the population, which is 1. Now, what's really interesting about this is that you'll notice that the standard deviation decreased. It went from 1.41 the square root of 2, to 1. So if you look at this, what is 1? Well, the 1 is square root of 2 over the square root of 2. That's equal to 1. And this is our standard deviation from our original population. And this is our sample size. So the central limit theorem now says that the standard deviation of your sampling distribution is equal to the standard deviation from the original population divided by the square root of your sample size. And this ends up being the most important piece of the central limit theorem. So now let's talk about how this plays into problems real quick, and I will end this video. So let's say I'm taking, we were studying, we had a normal distribution, and I had a mean of 700, and I had a standard deviation of 10, and I wanted to know what's the population I would get 750 or more. I want that probability. So I would go normal CDF of some sort, use that function. I would say, okay, my lower limit is 750, my upper limit is infinity, so one really big number. My regular mean is 700, and my standard deviation is 10. And I'd hit enter, and I would get some area, some probability that that was going to happen. Well, what if I said, what's the probability? I had this population, but instead of just finding a single one that was 750 or more, what if I wanted to find out the average of 25? So the average of 25 was 750 or more. And getting 1 over 750 maybe is fairly likely, but giving 25 people whose average is over 750 is going to be really small. So what I would do here is I'd say my new standard deviation of my sampling distribution, is my old one, 10, divided by the square root of 25, which is 10 divided by 5, which is 2. My standard deviation is much smaller now. So now I'm going to take normal CDF and go 750. My lower limit, upper limit still infinity. Mean still 700 on my new distribution, but my standard deviation now is this 2. And we end up that way. So that is how you're going to do all of these problems coming up on this week's homework. I hope you guys all have a great week, and I look forward to seeing you on Wednesday at our chat. Thanks so much. Bye.